Okay, so we are going to talk about the organic chemistry reaction mechanism. And this is a question that complete the mechanism of the following reaction, drawing the proper arrow in each step. And showing the proper arrow is showing your understanding about this problem. This one gives you a little hint about this. This is what they call the electrophilic substitution. But the one that what you learn throughout the organic chemistry portion in Chem 2, you should be able to have a good understanding about how this reaction should occur. So, so let's talk about the chemical reaction, and I would like to see the proper arrow means essentially about electron movement. Okay, and then typically when you have using this arrow, that means you are moving two electrons. And if I think the problem you didn't cover about that, this fish hook kind of one is talking about one electron movement. Probably you will learn in the second year organic chemistry class later on. But this time, probably we are more focusing on just regular arrow involving the two electrons and usually forming a bond. Okay. All right. So let's have a look at this molecule. This molecule has this pi electron, which is electron rich, and this is an HCl that likely dissociated with H plus and Cl minus. And then this one actually showed me that essentially this H was forming a bond on the bottom side and leaving the carbocation at the top. So how this one can occur is you would write H plus and Cl minus dissociation, and then this there is a double bond, has a two electron, and they are going to form these two electrons. We're trying to make a bond, and by making a bond, and you're creating new CH bond at the bottom. Okay, so that's what the reaction arrow should be looks like, strictly following the scheme. But I want to give you a little overview on this first step. Yes, actually this is about the options. Okay, so when they actually forming this compound, this double bond, you're trying to form the new CH bonding. They can form this way, or actually new bonding can form with the one in the top, and then they can form cation in the bottom. Okay, so we are talking about the carbocation in the cyclohexane ring, where the first one is in the what these people call, this is a tertiary carbocation. This is if you look at the one in the bottom, this is a secondary carbocation. And the most important one is the distinction is this methyl group is an electron donating group, and so the carbocation, which is has only 6 electrons, and they love to have a neighboring attachment, giving an electron donating group. So the electrochemistry, the stability of the carbocation rise. This is more stable. So that's how you can make an understanding. So this is the first step is essentially forming CH bond by opening the double bond, and then you lose a pi bonding and you form these structures. Okay, all right. So I just trying to combine this with a little mini lectures. So as first step is concerned, this is about stability of carbocation. Okay, and then with essentially something like CH3 electron donating group attachments. And you can think about if you have a CH with a CH3 attachment, that's what we call the primary, and then if CH2, okay, or if you have a CH with 2 CH3 electron donating group, that's what you call the secondary. And if you actually have a CH3, CH3, these are the 3 electron donating group. That's what we call the tertiary butyl group, and that's a tertiary group. And in terms of stability wise, that's how the stability is being ranked. Okay, so that's a little understanding for the first step that is involved here. So let's shift our focus onto the second problem, which is second portion is, okay, what about once this carbocation compound is being formed as a transient complex, transient species, and then you left with a chloride anion, and then looks like that they are trying to say the bonding between CH is being formed up there. And how do I understand that? And then in this case, you want to show, okay, this one has a 4 lone pairs, and then one of the lone pairs will go here and then make a bond so that they can form the new, and they can form CCl bonds. Okay, new bonds, and then that's how the reaction can be happen. So this is essentially very similar. This step is similar to reaction step. One of the reaction step in SN1, right? In the SN1, essentially the leaving group is left first to leave out this compound, and then the nucleophile is going to make a bond with a carbocation. And I think that if you look at now the Dr. Ma's the lectures, this is more like a plane, right? So this is what we call the sp2. This is an sp2 carbon, which is like a planar triangle. And so this carbon here is an sp2 planar triangle. So if I just focus on this portion, so I'll just make a dots here, and this is a methyl group, and they kind of nicely form the plane. And so then if you think about it, the chlorine double bond can go from the top, or they can go from the bottom and make a bond, right? So chlorine ions can make a bond here, and then they can form this bond. And so in this case, if I just finish that up, they will be forming something. When you're coming from the top, I think let's say, okay, this one going from the top, so bottom one will be CH3. And when you from the chlorine forming a bond from the bottom, and there will be like this chlorine, and the methyl group is going to be something looks like that. And then we're going to say, are they the same molecule? They are the same molecule. They're the same molecule. So that's why they show this way, because in other way, that what I want to say is this is not chiral center. Okay, so this is a second step. And what I wanted to actually discuss that, if I have this problem change it into a variant, And what about if I draw that? Okay, I can start the problem, but now in this time I am going to say, oh, there is a methyl here, and then there is a methyl. So it is a pretty much the similar situation, and the chlorine would need to make a reaction, and so that's why this is an sp2 carbon carbocation. This one can go to the top, or they can go from the bottom to make a new CH bonding. And in this case, and you are talking about this with, okay, the one going from the top, so chlorine here, that's methyl, and then the one in the bottom, which is methyl goes up, and the chlorine is coming from the bottom. Okay, so these two cases looks similar, right? But what is the difference is now we have this one, CH3, CH3. So therefore, I can start to identify, oh, this is a tetrahedral, right? This is an sp3 tetrahedral carbon, and you have 4 different attachment. So therefore, this is a chiral center, right? So these are what they call the racemic mixture is possible here, right? Because this is essentially 50% possibilities, and they will have a racemic mixture as a product. But if you look at the top portion, and this is the original problem that it looks like, and whether it is the chlorine from the forming a bond from the top or from the bottom, essentially this is not a chiral center, so essentially they are same molecule. So that's why I think your answer was given just like that, without showing that which way is going up and which way is coming down as in the notation. So that's a little higher levels of electrochemistry notations, and then I hope you actually understand even my variation to the problem to make this way and then that way. These two attachments are not the same, so you're having generated sp3 tetrahedral chiral carbon center. Okay, so so you have in this one, in the organic chemistry, they call it, oh, you ended up having racemic mixture because there's equal opportunity to react from the top or the bottom of carbocation, which is a planar sp2 carbon, and the bond or nucleophile can make a bond with a carbocation carbon from the top plane or from the bottom plane.